Okay, shall we start then? I will start with the session. So good afternoon, everyone. Welcome to the D216 Additive Manufacturing 1. My name is Tino Stanković. I'm coming from ETH Zurich, and I will be the session chair. So before we start with the pre-recorded presentations, I will just announce the presenters or the first authors. So the paper 1 is functional modeling in the design of additively manufactured components. That's will be presented by Enno Garrelts. Enno has a master's degree, and he is research assistant at the Institute of Engineering, Design and Industrial Design at the University of Stuttgart since February 2017. He is part of the research group doing methodical product development with focus on lightweight product development. His research focus is design for additive manufacturing. The second paper is supporting additive manufacturing technology development through constraint modeling in early conceptual design, a satellite propulsion case study. The presenter is Olivia Borgue. She is a PhD student in the group of systems engineering design at Chalmers University of Technology. She is working on the introduction of new technologies for on-orbit systems. Paper number 3 is conceptual design for additive manufacturing and explorative study. Presenter is Filip Valjak. Filip is a PhD student at the University of Zagreb. Currently, he is working as a teaching and research assistant at the Faculty of Mechanical Engineering and Naval Architecture. His research topics is the design for additive manufacturing for early design stages. And the paper number 4 is redesign of additive manufacturing spare parts based on feature classification. Presented in so nuclear mechanics engineer doing his PhD at the Institute of Technical Product Development of the University of Bundeswehr in Munich. Since 2018, he is a part of additive design team for the 3D printing center of the Federal Armed Forces in Germany. Okay, so I will ask Mario to let the presentations run.
Okay, I'm starting. And just one more thing, please, during the presentation, just everyone have your mic turned off. Okay, thank you.
My name is Enno Garrelts, and on the behalf of my co-authors and me, I'm happy to present our contribution with the title Functional Modeling in the Design of Additively Manufactured Components. Additive manufacturing can produce highly complex components. This is because there can be a high geometric complexity in the parts, and also because material properties can be adjusted, as can be seen here, where we printed a part with porous material. A high complexity of components does not increase cost for additive manufacturing. Only with conventional manufacturing, a higher degree of complexity increases the cost. An adequate application of additive manufacturing, therefore, always involves also a high component complexity. The question we asked ourselves was therefore, how should designers deal with the high component complexity of additively manufactured components in the early phases of design? Complexity is an issue in several areas. In product development, we deal with high complexity by decomposing the main problem and work on partial aspects of it. Functional modeling is used to do this decomposition. There are 3 methods that are mainly used: function lists, function trees, and function structures. But these methods might also help in the design of individual components. The hypothesis we tested was these existing methods for functional modeling help in the early phases of design for additively manufactured components. In order to test this hypothesis, we developed a design task. Students were given the supports and handed in their design sketches for evaluation. In order to not only evaluate the abilities of the individual students, but to evaluate how good the supports are, we introduced a second design task, which was done by the students previously, and no support was given for this task. We could then evaluate how good the support is by looking at the differences between the results. We not only had one group, we had two groups in order to also evaluate how hard the individual design tasks are. The design tasks were a hole punch and a stapler. Our evaluation criteria were explained to the students in a script they had to read before the tasks. We evaluated the overall orientation of the design components, if there are overhang angles that cannot be produced, if there's warpage, or if it's considered in the design not to have warpage, if the design is lightweight, if the design is functional, if the design is integrated in one or only few parts, if elasticity is dealt with in an adequate way in the design, and if moving parts or the connection of moving parts is considered well. Before coming to the results of our study, I wanted to mention some limitations. For one, we only had 32 participants, which is a quite low number. Second, we saw a decreasing motivation of our students. The scores reached in the second task was overall lower than in the first one. We also didn't see a significant influence of the methods for functional modeling. The students didn't increase their performance, but also they didn't lose performance. The second result that was quite interesting is that the hardest part for students is dealing with overhang angles, shortly followed by dealing with warpage. Lightweight design was the third hardest thing for the student. I'm looking forward to discuss our results and our study with you in the following discussions.
Hello everyone, my name is Olivia Borgue, and today I will present you the article called Supporting Additive Manufacturing Technology Development Through Constraint Modeling in Early Conceptual Design, a Satellite Propulsion Case Study, which was written in collaboration with Filip Valjak from the University of Zagreb and Dr. Massimo Panarotto and Professor Ulla Isaksson from Chalmers University of Technology. And I would like to start saying that successful products need to satisfy user and customer expectations, often articulated as required functions, while at the same time ensuring efficient manufacturing. But when introducing new technologies, such as additive manufacturing, the trade-offs between performance and manufacturing feasibility can be difficult to assess. For example, due to the promised design freedom and complexity for free, additive manufacturing potentially enables weight and lead time reductions. However, this technology comes with manufacturing constraints that limit the said design freedom. And such trade-offs are visible in any industry currently trying to implement these technologies. Due to the promised design freedom, design for additive manufacturing methods sometimes produce designs that are impossible to manufacture because of the current technology limitations. However, as additive manufacturing technologies are developed through, of course, long and costly research endeavors, these manufacturing constraints can be relaxed, and designs that were unfeasible before can become manufacturable. When we design a technology roadmap to target a future design that we want to develop, we can make design decisions today that will help us to progressively develop the capabilities necessary to reach a targeted design in the future. But the problem is that currently, the development of technology roadmaps and the estimation of the cost and development times involved are a bit subjective or based on experts' experience, we can say. which can lead to expensive and inefficient development strategies. And that's the reason why we have this specific research question, which is how can decisions about additive manufacturing technology development be supported in early conceptual designs? Basically, what is it that we can do right now in terms of design decisions that would put us in the right track and one step closer to reach the targeted end of our technology roadmap? And for this, we have proposed a design method, and we have tried it in the design for additive manufacturing of an electric motor for satellite applications. And in our method, we start with the function decomposition. We map the product functions with corresponding additive manufacturing design principles or capabilities. And then we develop two designs. One opportunity-based design, taking advantage of design freedom without concerning too much about feasibility. And this is the design that we will consider as a target in the technology roadmap. And then another design, which is a constraint-based design, focused mostly on current additive manufacturing capabilities. In the end, we have invited industry practitioners to compare these two designs. And we have together concluded that the key for establishing realistic technology roadmaps and the key to achieve a targeted design is to model constraints. Because if we model constraints, we have a structured and precise way to direct the attention to company capabilities that need to be improved or where future investment is needed. Moreover, we can establish intermediate profitable product architectures to include in our roadmap. We could say that determining a technology roadmap based on incremental constraints release can be the first step towards analytic estimation of cost and development times of technology roadmaps, which are currently missing from literature. Well, that's everything I had to say. Thank you for your attention.
Hello, my name is Filip Valjak, and today I'll present a paper called Conceptual Design for Additive Manufacturing, an Explorative Study. The paper authors are myself, Nenad, Bojčetić, Axel, Nordin, and Damir, Godec. The paper was written in collaboration between University of Zagreb and Lund University. In this short presentation, I'll present the research questions we investigated and related to the design workshop, as well as overall results of the study. This study is a part of our ongoing PhD research. As we all know, the development of IM technology changed how we manufacture our products, and this consequently changed the way we design our products and led to the development of DFM methods and tools. According to Paul and Binz, the biggest influence we have on the design of our products is in the conceptual design phase. Therefore, in this study, we focus on investigating the influence of IM on conceptual design phase. The main research question in this explorative study was to find out what is the current design practice in conceptual DFM process. Furthermore, additional question was, could the use of functional model be beneficial for IM-oriented conceptual design? Before presenting the study and the results, it is important to mention that there are few different DFM approaches focused on the conceptual design process at the moment. Some well-known are the design feature database, design heuristics, and the design principles. For this study, the most significant approach are the design principles, especially the approaches that are based on functional classification of principles. There are two main directions of principles development. First, the catalog of design principles, and the second are the computational repositories presented on the last ISET conference. As mentioned, in this study, we conducted a small design workshop with 6 experts from academia. All participants are designing IM products for both educational and industrial purposes. The workshop consisted of a design task that was done as a team activity, followed by questionnaire with questions about the task and participants' previous experience with DFM. Afterwards, there was an open discussion session about the design task, conceptual IM design, and the use of functional model and conceptualization, as well as general discussion about DFM and its applicability in both education and industry. The design task was to create IM concept of a citrus press. The participants were randomly divided in two groups. They were given a general description of the product as well as its functional model. They were instructed to create a concept by thinking about IM-based solutions for a particular function or a block of functions. The design activity resulted in two concepts that are solutions for a given functional model. It can be seen that both concepts incorporate some IM-specific solutions, but also use some features that are more suitable for conventional manufacturing technologies. When asked about it in post-task discussion, participants mentioned that they use those features because they do not gain any unique capabilities with IM, but reduce the overall price and manufacturing time by using conventional manufacturing technologies. From the questionnaire and the discussion session, we found out that the participants have a need for specific DFM methods and tools in their everyday design practice, and are using some of the DFM approaches developed so far. They also mentioned that they found the functional model helpful as they focused more on the functionality of the product and not on the detailed design. Furthermore, from the discussion we found out that participants have a problem of teaching students and design practitioners to think additively, but also they mentioned the lack of comprehensive sources of IM knowledge. From the conducted study and gathered data, we observed three key points of conceptualizing the IM product. First is the problem of thinking additively, or to say, to escape the traditional design mindset. The problem is especially noticeable in experienced designers with little knowledge about IM. Secondly, there is a need for specialized DFM methods and tools that will support conceptual design of IM products. And thirdly, the participants emphasize the need for comprehensive source of IM knowledge that can be used in conceptual design phase. The conducted design workshop gave us an insight in current challenges of DFM practice, helped us invent challenges that need to be addressed in future. Furthermore, the design task activity showed potentials of using a functional model in DFM practice, and further investigation of this phenomena are currently being researched. Thank you for your attention, and I'll be glad to answer any question in discussion session or by email. Goodbye.
Welcome everyone, and thank you very much for assisting this virtual session on the redesign of additive manufacturing spare parts based on feature classification. About the presenter, my name is Joaquin Montero. I'm a research associate and PhD candidate of the University of the Bundeswehr Munich. Our research field is in metal additive manufacturing with a specialization in the redesign of obsolete components, mostly spare parts for the defense industry, and we use reverse engineering techniques, agile hardware development principles, and design for additive manufacturing in order to obtain successful redesigns. So there are many benefits and many reasons of why to use additive manufacturing on the redesign for spare parts. For example, to keep running machinery whose spares are no longer in production, to do emergency repairs or provisory repairs, to improve faulty designs, reduce warehouse storing, or reduce lead time. Even though can be costly for some applications, those uses where budget is not a relevant factor are the actual interesting uses of additive manufacturing spare. For example, the military, when you need the spare parts quickly. So the goal of this presentation is to present a structural way to redesign for additive manufacturing and to highlight the necessity of communicating the IM limitations to the end user so that realistic designs can be achieved in common agreement with the designers. In order to do that, we present two different approaches in order to redesign for additive manufacturing based on a feature classification scheme or hierarchy. So we start with a classic data acquisition, 3D scanning, then we redesign based on this feature classification scheme. So we present the two approaches, and then we hop into the classical pre-processing, manufacturing, post-processing step process. So what are these feature classification? Okay, the features are the geometrical characteristics that compose a part and we divide it in 3 groups. The first group are the features that compromise the technical functionalities and compromise the performance of the spare part. The second hierarchy are the features that do not impact the expected function, but maybe are affecting the handling manipulation of the component in the assembly. And the features of third hierarchy are the features that have that are cosmetic or have some characteristics inherent to the former manufacturing method, for example, draft angles in casting parts or bending marks or die marks. Okay, so what is approach A? The approach A is a classic redesign or adaptation for AM process approach. So features 1, 2, and 3 are tackled with the same importance, and in approach B, only features 1 are prioritized, while feature 2 and 3 are included in the design only if the end user wants it. So the approach A is more constrained than the approach B, so it's more rigid, and the approach B is more flexible. So in the approach A, the part is finished when the part looks like the original, and the approach B, the part is finished when the part deploys the same function and is maybe optimized. So we can see here like a normal, like a 3D scan by the approach A deliver like a part that looks like the original, and the approach B is something that is actually optimized by the designer. Both approaches were comparing different spares, so we present here the results showing that the approach B overtook the approach A. Approach B overtook the approach A in design time, build volume, and superstructure volume. So what is the outcome from this result? So it is easier for the designers to exploit the capabilities of AM when they are more free to modify the designs, but this is commonly not encouraged by the end user, who expects some sort of photocopy of the original spare. So common agreement, prototyping, and feedback is key for the successful creation of AM spares. Thank you very much for attending to this presentation. For checking the results, feedback from the end users, and the formalized questions, please read the original article, redesign of additive manufacturing spare parts based on feature classifications. Thank you very much again for attending, and finish.
Okay, thank you for the presentations. Before we go with the discussion and questions, I would just like to make a small summary. So we had 4 very nice presentations, in which the paper number 1 actually and paper number 3 tackled the same question in investigating whether the functional model is or isn't beneficial for conceptual or for design for additive manufacturing. And in that investigation, paper number 1 stated that the functional modeling alone does not improve the student's design, whereas the paper number 3 stated that there is potential of using conceptual modeling to support design for AM. And also I have to stress out that the paper number 3 that people from academia and all 6 of them agree that functional modeling helps, okay, but only in the respect they were thinking in the respect of design process. Paper number 2 is different because it was investigating technology roadmap, but paper also concluded that the functional modeling is highly abstract. It does not conclude the means for fulfilling the functions, and that the AM capabilities, which are very important, should be stressed out and documented in a morphological matrix, which is somewhat the same with the conclusions of the paper number 1 that stated that the most difficult problem is how to deal with the design limitations due to the laser beam melting AM that was applied in their work with respect to the warping and other undesired effects. And finally, the paper number 4 is something different because it does not discuss the functions, but actually functional design in a sense of rationalization and offering optimized design to the customer, which is somewhat concurrent to the paper number 2 that also had 2 different studies with opportunistic and non-opportunistic designs. The conclusion of paper number 4 is that customers like the shapes they understood better, I think, in the end, and that the constraints are of additive manufacturing extremely important. They have to be explained and communicated to the customer, which is on the same line with the conclusions of papers 1 and 2. So we almost have a consensus on some points. So I would ask participants to ask the questions to the presenters. How do we do this? Let me see.
Okay, so participants can just press the blue button at the top of the screen and share audio and video, and then enter this session and ask a question.
Thanks.
Okay, I've got a question. This is George Fadel. So it's interesting to see the push on function and some of the work that we've done in the past. I've always had issues with functional modeling because for me, a functional model is really a transformation from an input to an output. And as long as you're doing something like that and you have that transformation, functional modeling is great. However, functional modeling does not relate at all to anything like size, shape, or anything like that. So I feel it is not really adequate to address many of the issues that are really at the core of additive manufacturing, where you can work with size and shape and features and things much more than what a function would allow you to do. So we came in with, we introduced the idea of affordances, and I wonder what is the right balance between function and affordance whenever we start thinking about designing, especially designing for additive manufacturing.
Thank you for the question. Whom do I ask first? Because there are three discussing functions. So let's start with paper number 1. So Enno, can you comment, please?
Actually, I'm translating affordance. I'm not completely sure in which respect to translate it to German.
Actually, it is a word that did not exist in English either. It's a word that was developed by a psychologist that says, what does a device afford the user? What does it allow the user to do with it? So for instance, an example, I think of speaker 3, where you had a lemon press or orange press. You can start thinking about what are the functions that you need to be able to do, but also you start thinking about how to interact with it, and then the affordances come in. You could accomplish the same function with a micro device or a major, huge device. So there is no restriction on shape from the function perspective, whereas with affordance, shape and size is much more important.
Yeah, I think this is one point we saw in our study, that functional modeling is really not the tool for everything. And I think the interesting difference in the two studies we took, the one of Filip's, they used a much more complex product, and I think also a product that's much more unknown to the participants. If I'm correct, I think my examples were widely known, and the functional modeling didn't help because the functions were not the real problem of the product. So you really have to find or look at your problem. Is the function of the problem? Is affordance? I don't know. Is the design maybe the problem? And you have then to wisely choose your tool or your method.
Thank you. Maybe Filip, could you comment
yes,
further?
If I may comment. Thank you, Mr. Fadel, for your comment. I agree with you, but what we found out in our study, when we gave the functional model to our participants, it was only 6 participants. It was all from academia, everybody familiar with pollen bites, so that's really important to emphasize. But we didn't give them any solutions for a particular function. What they explained to me later in the discussion session was that when they usually design for additive manufacturing, they often focus just on the outer shape, geometrical complexity, and so on and so forth. And what they say that they see that as a potential of using functional model is that they also they started thinking about shapes and everything, but they also went through the functional model that was given to them and tried to think, can I solve some other functions with additive manufacturing as well? Of course, without additional help, they didn't have a solution for every function by means of additive manufacturing, but they say that they see potential in stimulating their cognitive process and stimulating ideas by simply thinking, okay, I didn't solve this function, how can I address it in my design? So in some way they combine this affordance or the outer shape of the product with the functions they need to solve.
Thank you.
Presenters would like to address maybe the same question, Olivia or Joaquin. Olivia, please unmute yourself. Can't hear you.
Olivia, you can try to refresh the page. Just press F5 button on the top of your keyboard.
Wait a bit. Okay, Olivia is back.
Olivia, if you want, so you can just type your question or answer or whatever.
You can type, Olivia, I can read afterwards. Do we have more questions for the presenters?
I have a question.
Hey.
Hi.
Please,
Thank you. And I'm Serena Graziosi from Politecnico di Milano. Thank you very much for your interesting works in this field of AM. I'm curious about this aspect. So when we deal with additive manufacturing technologies, we also think about the digital workflow, okay? So the digital part of the design phase, the design process is extremely important. Digital and computational part of the design process. So my question is, could be other strategies to support concept design phase related to design for AM, involving, for example, artificial intelligence or some more complex algorithm that could support the concept design phase and in order to make the whole process as a digital process? I think it's a complex question, maybe.
Whom do you ask?
I would like to know the opinion of all the speakers, because
okay.
Maybe can I hop in here?
Please.
Yeah, please.
All right, yeah. As you mentioned, it's really important to understand the difference between digitization and digitalization. So in my case, I deal with the spare parts, and with the spare parts, you want to digitize your parts, or go from some analog stuff or like some drawings or even the physical part or even a picture to something digital. So you're digitizing your design. When you want to digitalize the process. So the processes get digitalized because you make it in a digital workflow, if you say, or I don't know, digital process. In our case, what we do, we are not enhancing anything with AI because our work field is super rigid. So the client or the end user before they go to you as a designer, they already know what they want. It's super hard to make it more flexible or to convince the client or the end user to have like a digital enhanced part, or even to have the digital spare. Normally we store the digital spare, we give them the physical spare. So it's super hard to actually implement, at least in the industry, to implement this concept of digital improvement on the digital spare. I don't know if in any other industry as of right now is easier to make it, but what we do normally is we have like some sort of, we use like Jira, the software Jira, to kind of create a digital process there. We have it online, we have deployed. So we have some guys doing different stuff in the different stages, and we can see how the digital spare goes through these different steps. So it's a sort of digitalization of the process with the digital spare, with digitized part, but it's not in any point enhanced by AI. So we are somehow limited by the end user. It's not that we don't want to do it, but we are somehow limited. So this is my input to your question. It might not answer it completely because my field doesn't, let's say, limits me to implement it to a full extent.
No, I understand. Yeah. I mean, my question probably is a bit broad in terms of perspective, of course, but on the other side, being you a researcher, you should try not to be too much influenced by your end users. That's another point. But I understand. No. I mean, I understand. It's okay. It's nice to find a compromise because, of course, a researcher must always take into account the background, of course, the context where they work, but they should also try to look forward. Let me say, but thank you for this very interesting perspective. Of course, I don't know whether the other participants want to add something on this.
If I may comment on your question or comment at the beginning, first of all, thank you for the comment. For example, Joaquin, he is more into detailed design and production of iron parts. On the other hand, my paper, as well as Enno's and Olivia's, is more into early design phases. And when I'm creating a concept, I still don't have a digital model, and because I'm still thinking about the architecture of the product. Here we can use some digital tools to improve the conceptual design, to try to find different solutions for particular feature function, depending on the area we are investigating. Here I think that what we also found in our study is that participants said that they have a problem of finding comprehensive source of IM knowledge, because every day we are still investigating additive manufacturing. Therefore, the digital tools here could potentially have a really big influence, because we could easily build up our repositories, our database with potential solutions, features, and so on and so forth. And by using some advanced machine learning, artificial intelligence, that could benefit the designer to limit the design space, or to maybe not to limit the design space, but rather to say to help them find the suitable solution for the given problem. Here is where I see the influence of digitalization, particularly in the process of storing IM knowledge.
Thank you, Filip. Thank you. Yeah, I agree. Yes, good point.
Do we have anyone else that would like to comment or to the question that Serena made?
Okay. Thank you.
Yeah, thank you, Serena, for asking the question. I mean, there is also a question. There is George here. There's also a question of data related with the data-driven. You know, where are we going to get the data to support all of this? You know, that's another point. George, do you have a question, maybe? Because
I don't know why I was kicked out, I guess, and I came back in.
Okay. Okay.
I was listening to what you guys are saying.
Okay.
I still think that digitization may be required at all steps of design, even from the early stage to the two redesign stages. I mean, some of the things that we may not consider, you take apart, you're trying to think about how to redesign it. You may analyze it and try to see where the stress lines are, and then rethink your design in terms of trying to make it lighter or stronger or whatever it is. So there are possibilities to possibly tie some of these analysis tools with AI tools and have them help the designer to figure out how to possibly modify their designs or come up with new designs.
Yeah, I also, I mean, definitely agree with this because, I mean, for instance, normal topology optimization tool is now, I mean, being used as a conceptual design tool, because if you design a certain load carrying element, put the forces, you give the domain, you get the design, and you will start from that point on, you know, so it flips the whole story, you know, before even writing the functions and other stuff, you know, related to that product. But that you're doing. But are there any comments to the what George just said, or we can continue? Okay. I also have something. You know, we started with the functional modeling at the beginning, and also linked what George talked about affordances. And when I read all of the papers, to me it seems that there is not much more in them except, you know, for part consolidation and lightweight design, you know. And I think there is much more in additive manufacturing than those two things. And in by saying that, you know, when I think about functional design and also the models that are more rich, like affordance-based model or models that consider processes in which you know, put the part in the interaction, or the product that you design in the interaction with the user, and have the whole perspective. And when you search for different effects that can actually help you create that special ingredient in the product that should enable to make a completely novel product, how can we introduce that knowledge from additive manufacturing? Because in most of the papers you noted out, there is a problem with AM knowledge. How would I access that knowledge? And that knowledge, that problem I don't find any different than the problem that we had before without additive manufacturing, when we said, okay, how we knowledge about the latest and greatest and functional, you know, in physical effects that can actually help me realize the process that I'm modeling using functions or any other mean. So any comments from the presenters on that? I think this is a key issue mentioned in many of the publications and papers that you that are presented now.
If I may comment, thank you, Professor Stanković, for the comment. Yes, I agree with you. The problem at the basic level is the same as we had with the traditional manufacturing, especially when I'm looking through my eyes of functional modeling. The difference is only that we have a new knowledge that we didn't have previously, and that new knowledge is based on the new technology that we are using. The only key difference is, for me, is that today that design knowledge that we used before for milling, drilling, and everything was built up previously while we still didn't have the computers, and then build it upon that knowledge. And the additive manufacturing is completely new technology that is really closely related with computational design, but also with computer-controlled machines, and that's why we maybe have only a new possibility to store it in new types of repositories. But at the basic level, it's the same problem as previously. If that's at least my understanding, if I understood your comment correctly.
I mean, yes. I mean, it's much more, I would say, because it's not only about manufacturing. I think there is a completely new series of technical solutions that you can do based on these technologies. Except
yes,
with respect to design of new materials that can actually help you design better, and all of these effects are not accessible to everyday engineers. I think that's the problem, because they would use that knowledge if they would have it. So that's not the question. That's not the question at all.
Yeah.
Any other comments?
Yeah, I have a comment for paper 4.
Oh yes, please. Paper 4 we didn't address a lot, as well as paper number 2.
I think the paper 4 is a quite interesting approach, but I have some questions about the figures. It seems like if you do the approach B, the design time is quicker, and I have really hard to understand why you do an optimized sort of part for AM is quicker to do than just a solid block, especially when you look at figure 4. How can that be possible?
This is exactly one of the key things that maybe is not well highlighted. The thing is with approach B, the designer who works on that, he already knows the rules. So he see the part and he already knows what actually has to do. We report 4 different parts. So the 4 different parts, we are not allowed to show them explicitly because we work in an industry which is super rigid. It has our military copyright, let's say, limitations. And the thing is the designer already know what is the feature classification, how does it work, and which features to neglect. That's why it's faster. It doesn't mean that the designer actually does the optimization in all the parts, but the optimization is basically done beforehand. So the designer already know, he see the parts and then he basically knows what to do. That's why it's so fast, because the training is already beforehand applying the approach. I don't know if that answered your question.
No.
No, okay, right. So the thing is, the picture I showed in the paper is an example. It's not like the original parts. So only the thing that the picture that is shown in the, I don't know, I have it here. Maybe I don't know if you can see. You are talking about this picture, isn't it?
Yes.
Okay, right. So here we show like how is the scan looking like and what is actually like the approach A, the classic approach, and then the approach B, the designer already knows what to do. So he already start with the optimized part because they know that which optimized, how the optimization works, or no. So it's that time is not taken into account. So that's why it's shorter, the deployment time. So,
but it's I mean it's still very hard for me to see that approach A should be slower. I mean, it must be typically something totally different.
The thing is like that's like when it's the approach A is slower basically because on the iteration system, when you they design the part and the part gets a little bit over constrained, and then when we print it and then we have to modify it again, then we had to basically do another design from scratch. With the part with approach B, we only parameterize the interesting feature, the feature that we know that might have some problems, and then we just modify that in the second iteration. So the iterations are faster actually. That is the overall time is shorter because the iterations are actually faster. We only modify the stuff that is actually, so like we know that it's gonna cause some problems. For example, I don't know, diameters of holes or threads, big cross sections, and this kind of stuff. And we don't have also to do any of the cosmetics in the approach B. That's why it's also faster. We don't have to put any marking, any casting marks, any stuff that is not actually necessary for the functionality of the part. So this is another factor that makes it faster and shorter.
Yeah, but I think that when you have an example that is totally different from the real part that you have designed or worked with, then it's going to be very tricky because it feels like, I mean, designing approach A in AM should take 15 minutes, and then you should do approach B in half the time or 75%. Then it's sort of 3 minutes, and that is impossible.
Yeah, we really explain that like super, with words because we are not allowed to show the original part. That's the problem. So basically, we kind of explain it with words, but on the picture is something just a schematic. It's not the real parts that we report on the graph. Like we report the data. So this is mainly, yeah.
But it would have been interesting to see a part that is sort of similar to. I mean, it could be a completely made up part, but it's at least similar to what you're talking about. Otherwise, it's very hard to see.
Yeah, I understand your question, but we did it like actually a couple of times, and we got the parts rejected because they were looking like very similar, and we were giving hints to which subsystem belongs to. So yeah, but I understand your concern.
Also, build volume is not that interesting, is it? If it's not very, very expensive materials, because it's often the time in the machine that is expensive. So you didn't mention the time in the machine. I mean, the build volume is a bit less in
exactly.
many of them because you create holes, etc. But the cost in the machine is often the
we say actually in the paper that we didn't report the time on the machine, and also because it's depending on the part geometry. And the parts the machine we're using is like a laser powder fusion. So basically, if you have like a bigger build volume in these machines, are like in this machine especially that we have that use like some specific scanner strategy, is giving you like straight away like a longer building time. So building volume and building time is kind of linear. So that's why I reported that. Is actually mentioned on the paper. But yeah, it's another good remark. We use by the way, the SLM 280. So it's a powder efficient system.
If I can comment on that, we made the same experience. We also calculated our costs for SLM first with height and build volume stuff and everything. And with some years of experience, I can say that it's mainly the build volume. All the other parts are neglectable, basically.
Yeah, especially with the last update. The last update is making like a double contour around the parts, so that makes even more linear this build volume overall costs, because it's with the time and basically amount of powder is getting into the machine. With a new update from March this year for the SLM brand especially, it's more the correlation even more linear than last year.
Answer. Peter, do you have more questions? You're good. Okay, thanks. I would like to ask Olivia, did you manage to connect? Because I still see some strange artifacts there, but yeah, we can't hear you, Olivia. Okay. Then I won't ask any questions. Just a quick question for Joaquin. Because we have still some time. So I talked to some people from Germany, and it seems that redesign of additive manufacture spare parts, but not only redesign, it's I would say replication of spare parts just for the sake of spare parts using AM technologies, because the original manufacturer does not exist anymore, is quite often now, and especially with the large companies such as Deutsche Bahn, for instance. And just as a comment, I mean, of course, you are in the defense industry, so you have outside suppliers, but they do it by themselves. so there is no problems, with respect to introducing the complexity that you had to do, because they also replicate, but it's inside. Is it possible that military does something like that, or it's always outsourced?
No, actually, it is possible because I don't know what is with the other militaries, but like with the Australian military and German military, there are some institutes that belongs to the military that they deal with this kind of subjects, as is our case. So we have like a 3D printing center in the military.
Okay.
And we provide services to external companies. For example, some companies building some tank, for example, they need some parts like normally are casted parts or forged parts. Because they don't have the original machinery anymore to produce them. So they request us as a let's say as a center, 3D printing center of the military to produce the parts.
So the same problem happens.
Yeah. So it's basically they request the client or the end user to produce the part. It's a little bit crazy, I would say, how it works. But mostly because of the copyright problems, they can outsource that to some other companies. So if the things, let's say, are kept in the family, it's easier at the end. Yeah, and regarding the redesign word, redesign is a very, let's say, not easy going word, because can be actually redefined or defined in many ways. What we do normally are like some sort of reverse engineering process, and then we do a redesign. We don't do a replication because the replication will infringe some parts of the Patent Law Act. So we try to avoid this replication or this replica mindset. We call it redesign basically because of that. It's because of the patent infringement. So that's why it's called a redesign, and why we focus mostly in the, let's say, like the parts that are functional and the parts that are easy to parameterize. Sorry. So this is why we use the word redesign and not replication or or adaptation. Some people use adaptation. For example, the guys from Renishaw, they use the word adaptation a lot, or adaptation for AM is like a kind of a science. But at the end, it's just basically redesign by using design for AM principles. So it's still being like a redesign. So you create a part from scratch by following some sort of rules of thumb.
Okay. Thanks. Okay, I think that we are, thank you for your answer. Almost out of time, so just before we leave, thank you to all of the presenters. Unfortunately, Olivia could not connect, so I suggest that each one of us find her later at the social gathering and ask her questions directly there. And just to wrap up, so we found out that more rich functional modeling is required to support design for additive manufacturing. So models or methods such as affordances, that the digitalization of the process is favorable and should be done throughout the whole of the design process. And we also discussed a bit, touched the problem of the knowledge, but we didn't actually say how we can make that knowledge about DFAM on all levels of I would say, scale available to the engineering designers, which is required to design better for AM. So thank you everyone for participating. Thank you to the audience, and thank you to the presenters.
Thank you.
Thank you. Bye.
Bye.